my earlier video, I had discussed about irreducible element and prime element of a ring. Today, I will discuss new type of ring, Euclidean domain. Euclidean domain actually the integral domain. In Euclidean domain, here some new condition has introduced in integral domain, which can have actually the Euclidean size function. Actually, the idea is consider a set D which is integral domain. That means obviously D is commutative ring without zero divisors. An integral domain with at least two elements. If there exists a mapping del which is denoted as delta from D to Z, here Z be the set of integers such that condition 1, for all non-zero element in the domain, then the image of this element always will be greater than equal to 0. Are you getting the condition 1? For all non-zero element in the domain, the image of this element always will be greater than equal to 0. And second condition, if we consider two non-zero element in the domain, consider two non-zero element A and small b in the domain D, then delta AB, image of these two elements always will be greater than image of delta A. Similarly, or image of AB can be always would be greater than image of B. Okay. Third condition, if we consider two non-zero element A and B, then their product always would be non-zero because the ring D is an integral domain. Fourth condition, for all A belongs to D and for all non-zero B, there exists Q and R in the ring D such that A equal to BQ plus R. This is actually the division algorithm where either the remainder equal to 0 or this relation delta R obviously less than not equal to, here only less than delta B. Okay. Here this mapping delta is called as Euclidean variation. See the definition of Euclidean domain. The definition of Euclidean domain is, let R be an integral domain, then R is said to be Euclidean domain if there exists a function delta from every non-zero element of this function to a non-negative integer of the ring R such that condition 1, delta A always less than equal to delta AB, where A and B are both non-zero element of the ring R, and condition 2, division algorithm, consider an element A belongs to R and one non-zero element B belongs to R, then for some element Q and R such that A equal to BQ plus R, and this is the division algorithm, then either R equal to 0 or delta R less than delta B, and here the function delta is as Euclidean variation. Are you getting the definition? Oh. Now I will see some couple of example of Euclidean domain. Example, consider set of integer, and I will prove the set of integer is an Euclidean domain. For this, consider a mapping delta from Z excluded the singleton set 0 to natural number union singleton set 0. Here the mapping is defined as delta from z to absolute value of z. Here absolute value because here the all positive integer. For all a which is non-zero be the member of integer. Also consider for all b which is also non-zero and member of integer. Then here the image of a would be absolute value of a. Then image of ab would be absolute value of ab. And obviously we all of us know absolute value of a always less than equal to absolute value of ab. That means delta a less than equal to delta ab. Since here the element be member of integer, so obviously this satisfy the division algorithm. Let a be member of integer and b be any non-zero element which is also member of integer. Then by division algorithm there exists obviously q and r in z such that a equal to bq plus r, where either r less than absolute value of b or the remainder is 0. And from this line we can tell easily mod r less than mod b. Therefore delta r less than delta b. Therefore all condition of Euclidean domain has satisfied here. That means the integral domain set of integer is an Euclidean domain. Are you getting the proof? Now I will say if f is a field, then f is an Euclidean domain. For this, consider f is a field. Then for field, every non-zero element has multiplicative inverse. And here, for all a belongs to f, define a function such that delta a equal to 1, where for all a belongs to f. That means here all non-zero element of the field map to 1. Now, for all non-zero element a belongs to f, also for all non-zero element b belongs to f, then their product means delta ab map obviously the function, the element 1 by the defined function, because here the function is defined as all non-zero element map to 1. Then if a not equal to 0 and b not equal to 0, since f is a field, that imply obviously f is an integral domain. Therefore, since f is an integral domain, that means their products obviously not equal to 0, because in integral domain contains no divisor of 0. Therefore, obviously the mapping delta AB equal to 1. Assume this as a equation 1 and this as a equation 2. Then from this, obviously delta A less than equal to delta AB. Therefore, the condition 1 of Euclidean domain has satisfied here. Now condition 2, consider a arbitrary element A in the field F. Then consider a non-zero element B in the field F. Now consider A equal to QB plus R. And if B belongs to the field F, since in the field every non-zero element has multiplicative inverse, that means obviously B inverse belongs to the field. And we can write A as A times 1 plus 0. And since B inverse belongs to this field, therefore 1 equal to B times B inverse. Therefore, now the equation has A equal to AB inverse times B plus 0. And this equation is look like A equal to QB plus R, where Q equal to AB inverse and R equal to 0. That means we are also satisfied the relation delta R less than equal to delta B, because here delta B equal to 1 and delta R equal to 0. Therefore, the condition of Euclidean domain has satisfied here. Therefore, if F is a field, then F is an Euclidean ideal domain. Since field is an Euclidean domain, so if we consider ZP where P is a prime number, since this is field, obviously this is an example of Euclidean domain. Similarly, if we consider real number, complex number, rational number, q square root of 2, q square root of 3, q square root of 2, square root of 3, both are field. So obviously these are example of Euclidean domain. Are you getting? Next example, the polynomial ring fx is an Euclidean domain where f is a field. For this, the mapping considered as delta, which map from capital D excluded singleton set 0 to set of positive integers, and the mapping is such type delta equal to degree of this function. Obviously, degree of fx greater than 0. To prove Euclidean domain, notice delta of fx comma gx always greater than equal to delta fx, because always degree of two polynomial greater than equal to degree of single polynomial. If gx would be constant, then this is just equal to, but obviously this would be greater than equal to. Okay, consider two polynomial fx gx which be non-zero polynomial. Then we can write by division algorithm fx equal to qx times gx plus rx, where either rx equal to 0 or degree of rx less than degree of gx. Okay, condition of Euclidean domain has satisfied here. So, if f is a field, then f is an Euclidean domain. Similarly, if we consider the Gaussian integer, then here the mapping will be defined as delta, which is defined, here the notation is delta, which is defined zi excluded singleton set 0 to natural number included singleton set 0. Here the mapping is look like delta x plus iy equal to x square plus y square. And obviously, if you check similar to before, this would be Euclidean domain. Check it oneself. Similar to before, I will see one nice theorem: Euclidean domain always imply PID. And the theorem is such type: let D be an Euclidean domain and I is an ideal. If I contain only singleton set 0, then I is generated by 0, then that imply I is principal ideal. Now, second condition is consider I not equal to singleton set 0 and consider a non-zero element in the ideal such that degree of A is minimum. For Euclidean domain, I have considered such function. Then, since degree of A is minimum, then I is generated by singleton set A, then there exists for B belongs to I such that Q and R such that there exists Q and R such that B equal to AQ plus R, where either R equal to 0 or degree of R less than degree of A. Okay? And from this line it implies B minus AQ, which is equal to R, which obviously belongs to the ideal I. Notice either R equal to 0 or degree of R less than degree of A. But I have considered degree of A is the minimum. So, degree of R less than degree of A, this cannot possible. That means only possibility is R equal to 0. R equal to 0, that implies B equal to AQ. Therefore, from this line obviously, B belongs to ideal generated by A. Therefore, here I have considered arbitrary element B from the Euclidean ideal domain. I have seen B belongs to particular one ideal, which is PID, because this ideal is generated by a single element. So obviously every Euclidean ideal domain is a PID. Are you getting the proof? Oh well. Today I will stop Euclidean domain here. I will briefly discuss this topic elaborately in my next video. Discuss UFD of a ring. Now we will review one question of ring theorem which had come CSIR Net June 2017 exam. The question is, let R be non-zero ring with identity such that A square equal to A for all A belongs to R. That means here every element is idempotent element. Then which of the following statement are true? Option 1, there is no such ring. Option 2, 2A equal to 0 for all A belongs to R. Option 3, 3A equal to 0 for all A belongs to R. Option 4, Z mod 2Z is a subring of the ring R. This is very easy type question. The ring in which every element is an idempotent element. That means this ring actually the Boolean ring. That means this is exercise of Boolean ring. Option 1, there is no such ring. This is wrong option, because if we consider the ring Z mod 2Z, this is obviously Boolean ring. Okay, so we can consider other type of Z mod 2Z, direct product cross Z mod 2Z up to. This type of example are Boolean ring. So first option is wrong. And option 2, obviously true option. Here 2A equal to 0 for all A belongs to the ring, because we all of us know characteristic of Boolean ring. If we consider Z mod 2Z, obviously this is 2 for all A belongs to R. Option 3 is wrong option, because if we consider the ring Z mod 2Z, then 3A equal to 0 for all A belongs to R, this is cannot possible. So this option is wrong option, and option 4 indicates Z mod 2Z is a subring of R. This consider a ring homomorphism F from Z to R such that the mapping is defined as f of x equal to x times 1. And this is equal to just 1 plus 1 plus 1 x times, and obviously this is the ring homomorphism, because here f of x plus y equal to would be x plus y times 1, and this is equal to x times 1 plus y times 1, and this value would be f of x and this value would be f of y. That means f of x plus y equal to here f of x plus f of y, and f of xy would be xy times 1, and this is equal to, we can write as x times 1 times y times 1, and this is actually f of x times f of y. This mapping is ring homomorphism, and fz is a subring of the ring R, because fz equal to x times 1 where x belongs to R, and this is equal to 1 plus 1, which would be equal to 0, because here 2x equal to 0 for all x belongs to R. That means this is actually would be 1 0, which is isomorphic to the ring Z2. That means option 4 is a right option. Z mod 2Z is a subring of the ring. I will stop here, and in my next video I will discuss this topic also elaborately. But at first I will highly recommend you, please see today's video is pay attention, because this video are more important to understand the ring theory elaborately. See you soon, stay safe and stay positive always. And don't forget to subscribe my channel. Thank you so much.